Hi, everyone. My name is Alon Levi. I'm a software engineer on the Google App Engine team. And this talk is called From Spark Plug to Drivetrain, Life of an App Engine Request. Throughout the course of this talk, you can go and use Google Moderator, which is an application built on App Engine, to submit and vote on questions, which I'll then answer at the end. If you're interested, go to code.google.com/events/io/questions. Click on the App Engine track in the middle, and then the title of this talk should be on the left-hand side. So this talk is called From Spark Plug to Drivetrain, and what I want to do is take a look under the hood of App Engine with you guys and see how App Engine works, see how the App Engine infrastructure works. This is not a talk about how to build App Engine applications. There are a number of other talks throughout the course of the conference that are going to cover that. But as a software engineer, I find that when I understand how things work under the hood, it makes me a little more confident and a little more comfortable working with the system. So with that, I want to get started. So the first thing I want to talk about is designing for scale and reliability. Not necessarily App Engine-centric, but just talking about what makes a web app stack scale. And we'll take a look at the LAMP stack and look at some of the principles there, although they apply to other web infrastructure as well. Then I want to take a look and talk about some of the lessons learned from sort of the progression of that LAMP stack and see the lessons that we applied while building App Engine. And then we'll take a look at some of the some different kinds of requests and as they pass through App Engine's infrastructure, and how that affects the way you design your application and the way your application actually runs. Then I'm going to go back over the design motivations and take a look at that in more detail. And then I'm going to go over some numbers regarding App Engine. So first off, let's talk about web stacks. So this is a very high-level overview of the Google App Engine stack. It's really exciting because it's something we haven't shared publicly before. You can kind of see that it's a standard three-tier web topology. You've got your front ends or routing on the left side, your application layer down the middle, and on the right side, we've got our persistence layer and other APIs. To draw to something similar that you guys may have seen, this is a slide from a talk Brad Fitzpatrick gave about LiveJournal in 2007, talking about how their progression through the LAMP stack and how they made it work for them. So as you can see, it's sort of similar to what we have going on with App Engine. You've got their Perl reverse proxies, which are their front ends in blue, application servers, application layer in green, and then APIs and persistence in red. So before we talk more about App Engine, I want to take a step back, or way back, and talk about web infrastructure in general, starting with the very basic LAMP stack. So as many of you know, LAMP stack is Linux, Apache, MySQL, and originally Perl, but it could be any programming language. In this, the very basic LAMP stack, you've got one machine running an Apache web server with Perl and MySQL database, all in one machine. So when a request comes in from the network, it hits this one box. Apache serves the web request, turns up a Perl instance, which may or may not make calls to MySQL and returns the response. This is a great start and a nice way to start building web applications, but it's not very scalable. You have a shared machine for your database and your web server, and very soon you'll realize that your database is consuming resources which your web server could be using to serve live traffic. Additionally, this is one single machine. If you have to do any upgrades or if there are any failures, you're basically out of luck. The next step is to take your database and move it onto a different machine. This frees up some resources for your web server. Pretty much the same. It requires a little bit of management and configuration for MySQL, but not too much. It's fairly straightforward, and it gives you it frees up part of your web server to serve more traffic. So this is sort of the next progressive step in building your web stack. So this scales up to the amount that your one Apache server can handle in web traffic. But you've now got two single points of failure. If either your database or your web server goes down, you're not able to serve traffic. So the next step, which you'll probably run into because have exceeded the amount of traffic that one web server can handle, is that you'll take your web server and split it onto multiple machines. This allows you to serve more traffic than one machine is able to. Obviously, you have to do a little more. You have to get some more machines, but additionally, you have to set up load balancing because you have to get the requests to different application or different web servers. One way to do this that many people use is what's called DNS Roundrobin. What you do is you register a list of IPs with the domain name server. So when your host name is looked up, one of the set of IPs is returned, and from the domain name server routes the request, or tells the client to route the request to one of your front ends. This is a sort of statistical load balancing. It's not dependent on the behavior or application. It's just spreading requests evenly across them. So one other thing that you do when you set this up is that you, when you register your record with DNS, you give it a time to live, or a cache time. This is great for DNS because it allows them to hold on to your configuration for a while before having to check to see if it's changed. But the bad news is that a lot of name servers won't respect your configuration. And what this means is if one of your web servers goes down, now you have to wait for DNS changes to propagate. And that may take a long time to reach all the name servers. So is it scalable? Yeah, it's pretty good. You can turn up as many web servers as necessary, and as long as your configuration isn't changing, you're good to go. But you're still I/O bound on one database. Additionally, like I said before, because of DNS Roundrobin and how long it takes to update your configuration, you can't redirect your traffic quickly. And of course, your database is still a single point of failure. The next step is to add what's known as a reverse proxy. What this will do is it will take requests from the network and then do routing and load balancing inside your network, or inside your application stack. This is a machine that you control that runs in your network. It allows you to do custom routing, and additionally, it allows you to use specialized backends, because this reverse proxy can be aware of the configuration that you're running and can route different requests to different backends. So here, for example, we see a request coming in, hitting the reverse proxy, and then based on whether it's a request that requires static content, it's routed to the static content server there on the bottom, or it's routed back to the Apache web servers for serving other kinds of content. This also allows you to do application level load balancing, because your reverse proxy, for example, in the LiveJournal slide I showed earlier, they were using ProBall, can be aware of the load characteristics of your web servers and do sort of a least loaded type load balancing policy instead of round robin. Requirements for setting this up: you're going to need more machines, and you're going to need to do some configuration and maybe write some custom routing code for your reverse proxy. This works really well. ProBall and many other reverse proxies are very robust. They allow you to do specialization, which is great because specialized backends are generally more reliable, and since they have to do a smaller breadth of work, they do it a lot more effectively. You're still bound by the routing capacity of one reverse proxy. You can add more, but then you get into the same issues we saw before with DNS round robin and not being able to change your routing policy quickly. You can get around that with fancy network routing hardware, like a hardware load balancer, but those things are very expensive and out of the reach of most basic level developers. Reliability-wise, you get agile application level routing. You can move application servers, turn them up, turn them down, move your load around very, very quickly because you control the routing infrastructure. You get to use specialized components like the static content server we saw on the previous slide, which allows you to have more robust backends. And again, we still haven't addressed the issue of the database, which is still a single point of failure. So let's talk about that. The next step, you would take your one MySQL database running on one machine and spread it out over to multiple machines into what's known as a master-slave configuration. This gets you a better read throughput, and it's invisible to your application. Rather, you don't have to change the way your application functions or accesses the database in order to make use of this. It's pretty much transparent. Requirements, obviously, you have to get more machines, and you have to reconfigure MySQL. But in general, it's pretty straightforward. Is it scalable? Well, master-slave MySQL, or master-slave for most databases, scale with the number of reads, or sorry, it scales the read rate with the number of servers, but not the write rate. So here we can see, oops, this is weird. Okay, well, I'm missing a slide, but if, for example, you had 400 reads per second, 400 writes per, or sorry, if you had 200 writes per second and 500 reads per second on one machine, and you spread it over to a master-slave MySQL, your reads will be able to hit any of the backends, so you can spread them across different machines. But your writes will they all have to go through the master and then be replicated through to the other database servers. So this is great for scaling up your reads, but as your application gets bigger and the net throughput of writes that you're doing also increases proportionately, you're going to soon exceed the capacity of one database server. And at that point, you're sort of out of luck, and you'll have to move to a different configuration. Regarding reliability, the master is a single point of failure for writes. If it goes down, you're no longer able to write to your database. And additionally, the master may die before replication. So as I said, when you issue a write to your database, it hits the master server first and then is replicated out to the slaves. If the master goes down after writing and before replication, you may lose a small window of data, which is unfortunate. The next step in scaling up your database is to use what's called a partitioned database. Effectively, what this is you take your master-slave MySQL database or master-master or any variety of configurations and split it up into different database clusters. This is done by a variety of different enterprise-level databases. This is the way that BigTable and the App Engine Datastore work. And additionally, Oracle Clustered and DB2 Federated work this way. It gives you an increase in both read and write throughput, which is great. But the downside is that it's a lot of work. You need a lot more machines. It requires a lot more management, obviously. But more importantly, you're going to have to re-architect your data model to be partitioned. The inherent assumptions that you have that all the data is stored on one machine or locally in one cluster and you can do things like joins or in-memory operations, that doesn't exist anymore. So you may have to rewrite your queries in order to take advantage of this. So this brings us back to the App Engine stack. So again, we have the front ends on the left side. They're basically App Engine's reverse proxies. They do application-level routing and load balancing. In the middle, we have our app servers and our static file serving infrastructure, which are responsible for serving those respective parts of an application. And on the right side, we have our data store built on BigTable, Memcache, which is something many of you may be familiar with. And on the bottom, we have some other APIs that your application may make use of. So now I want to talk about, given the progression of infrastructure we saw before to scale up a LAMP stack, I want to talk about some of the motivations and design decisions that we took into consideration when designing App Engine. The first was to build on existing Google technology. We didn't want to reinvent any wheels, and Google spent a lot of time building and designing scalable web infrastructure and applications, and we wanted to use that experience and use that infrastructure and make it available to all developers. Additionally, we wanted to provide an integrated environment. We wanted you to be able to manage the entirety of your application in one place. We wanted to encourage small per-request footprints and additionally fast requests so that we have high turnover of requests and not have to keep too much stuff in memory. That allows us to do the serving of applications without using virtualization. It's all on what's more similar to a standard web server than a giant clustered virtualization or a pool of virtual instances. We wanted to maintain isolation between applications and between applications and Google, so you can be assured that your application is safe from other applications, both security-wise and performance characteristics. If another application is burning tons of CPU or doing things like that, it won't affect the way that your application performs. We wanted to encourage you to write applications with statelessness and specialization in mind. Like I said before, using specialized backends gives you huge advantages, and having stateless requests means that we can do load balancing and application routing on a much more efficient scale. Additionally, we wanted to require a partition data model. I spoke earlier about how it's a very difficult step to go from the sort of regular database or master-slave or master-master MySQL to a partitioned paradigm. So we sort of make you write for the App Engine Datastore from the beginning. And in that way, you don't have to re-architect your data when you get to that stage. So now let's look at the life of some requests and see how they interact with the different parts of App Engine and what goes on there. So request for static content. The first thing that happens in a request for static content, or any request, is that it's routed to the nearest Google data center over the internet, and from there travels over Google's network to reach our App Engine front ends. This is a huge advantage. Basically, your application is running on the same network and gets the same advantages as all the other Google products, such as web search, Gmail, and everything else. You may notice decreased latencies for this reason and other good characteristics. Basically, you get lots of advantages just by being on this network. The next thing that happens once your request reaches the App Engine front end is the front end does load balancing and routing. In this case, since it's a request for static content, that request will get routed to the static content backends. And so this is a specialized piece of infrastructure that is wholly designed to serve static content and do it very effectively and very efficiently. And more importantly, as you can see in this diagram, your request has not touched the app servers or the other parts of your application that can be serving other traffic independently. So static content servers built on shared Google infrastructure. This is an entire service inside Google of which App Engine is not the only customer. And you can be assured that it's a very reliable, very robust, very large-scale system. This also means since your request did not hit your application servers or any of the other components that I talked about earlier, the files that are on the static content serving are actually physically separate from the other files that you deploy with your application. What this means, and something that some people observe when using App Engine, is that when they deploy their application and then try to access files which they've marked static, they're not able to do so on our app servers because those files are not actually deployed to them. So that begs the question, which content is static? Well, you tell us in your configuration which you upload along with your application. For Java, or for the Java runtime, the appengine-web.xml file, anything inside those static XML tags is uploaded to our static content servers. And in Python's app.yaml, anything marked static directory or static files matching those regular expressions will be served off static content serving. So afterwards, the response is returned from the static content server to the front end and then back out to the user. Again, we haven't touched any of the other infrastructure here, which is really great for scalability. So the next request I want to talk about is a request for dynamic content. So to do that, I need to talk about a few different components that I haven't brought up before. One of which is the App Engine AppServer and the App Engine AppMaster. So the AppServer is basically our web server. Its job is to serve dynamic requests. When you do computation or do API calls or do anything in your application outside of the scope of a static request, it ends up at the app server, and the app server is responsible for managing those requests. The AppMaster is another piece which is a little bit different from what we saw before in the standard scaled-up version of the LAMP stack. Its job is to manage and schedule applications on app servers. Additionally, it informs the front ends of where those what applications are scheduled on which app servers, so they can be routed. So requests can be routed. So a little more detail on the app server. App servers serve many applications, many applications, and they also serve many concurrent requests. So harking back to what I said about some of our design motivations, smaller app footprints in terms of memory and CPU plus faster requests allow us to serve more applications more effectively and make better use of resources. The app server is also responsible for enforcing isolation between applications and between applications and Google. This keeps apps safe from each other, and additionally, it keeps us safe from apps. So it also enforces statelessness, which is really important because since we don't know what your application is doing or what state it needs to maintain, if an app server goes down or if there's some other issue and we need to reroute requests or traffic, we don't have to transfer any state. You use your APIs to maintain state, and they're stored on a different piece of infrastructure entirely. So applications can be rescheduled or traffic can be rerouted across app servers without having to worry about moving state around. And then, of course, the app servers also service API requests for your application. So the first step in routing a dynamic content request is at the front end. Any requests that don't match static requests and match one of the other regular expressions in your configuration get routed to the app servers. The app server checks to see if there's a runtime in the cache, and I'll talk about it a little bit more in a second. If that exists, it uses it. Otherwise, it turns up a new runtime for your application, executes the request, and then holds on to that runtime in memory. This is a really important part of App Engine because it means two things. First of all, your first request to an App Engine app server may be slow. We may have to do a little bit more overhead to get your application up and running the first time, but then subsequent requests are likely to hit that cache. The front ends are designed to maximize this sort of caching. But the second and more important benefit for you all is that because this request, because the runtime hangs around in memory, you're able to use that memory across requests. There are no guarantees it will still be there. The cache may be evicted at any time, but you can optimistically cache either things that are expensive to initialize or compute or import or anything like that in your runtime, and it may be there when your next request comes in, which is really nice. So the next type of request is a request accessing an API. This is inside the scope of a dynamic request, but if your request decides to make an API call, it requests permission from the app server, and then the app server will block the runtime of your request, issue the API call, and then wake up the runtime again with the response. This is really cool because it means you don't have to manage concurrency and threading on your own. It's managed in the app server for your app. And because your application is stateless, we don't have to worry too much about what your application needs when it wakes up. We just hand back the response, and you're good to go. You can use APIs to do things that you wouldn't normally want to either do in the app server because you have limited resources or because you don't want to rewrite them for yourself. We have a lot of APIs that do a lot of specialized tasks, and now I want to go through and, well, here's a few of them. So Memcache and the Datastore we have talked about a lot. URL fetch is our API for fetching content from the web. There's the mail API. And then two new ones that we haven't really talked about before are the XMPP API, which is on our roadmap. Kevin talked about it this morning. And then the Task Queue API, which is for offline computation, which is something we're really excited about. And there's a talk later in the conference about a look ahead at offline processing for App Engine, which I encourage you all to go to. Additionally, we have images and users. So first API I want to talk about is Memcache, or our flavor of Memcache, Memcache G. So Memcache is a distributed in-memory cache that's used across the industry fairly heavily. Many of you who work with LAMP stacks and things like that may be familiar with it. The more common variant of Memcache is called Memcache D, and it was written for LiveJournal by Brad and the folks there to get better performance out of their in-memory cache. So Memcache G, which is the version we use, was also written by Brad and adds a couple of extra API calls that you may not find in Memcache D, which are batch API calls, such as set multi, get multi, and add multi, which allow you to incur the overhead of doing RPC less often. Basically, you can use Memcache to optimistically cache data in memory on a set of sharded servers for optimization. Things you might want to cache in Memcache are the results of database queries, the results of an expensive call to fetch something from the internet, or something that just requires a lot of computation on your application. You may want to hold on to it and not have to do it on every request. Memcache is a very specialized backend. It's just an in-memory cache. And that means that it's very stable and very robust. Things in Memcache may hang around longer than you would necessarily expect. BigTable is the next, or rather, the App Engine Datastore, which is built on BigTable, is the next API I want to talk about. And it's our API for doing persistent storage. Like I said, we want to maintain stateless requests and stateless applications at the app server, so you need somewhere to put your persistent state where you'll be sure it'll be there when your next request comes in. And for us, that's the App Engine Datastore. I spoke a little bit before about partitioned data stores and the advantage that those give you with regard to read and write throughput. We don't want to make you jump through the hoops of partitioning your data once your application gets to a certain scale. So and because we wanted to use BigTable, we make you design for this type of database from the beginning. You can use entity groups in your application to control your partitions. You may also have to define explicit indexes for your data store entities so that reads are instantaneous. We don't want to do a lot of computation on reads, so everything has to be a quick read from the database with no complicated in-memory calculation. Additionally, we have to update those indexes when a write comes through. So you might see that writes will be a bit slower. Because we're built on BigTable, you get a high degree of replication and fault tolerance. As soon as your mutation on your data store mutation commits, you're guaranteed by the time that API call returns, your data has been replicated to at least 3 machines. And this is without you having to do any extra work. The reason for this is that the data store is built on BigTable, and BigTable is built on GFS. Both BigTable and GFS have white papers on research.google.com, which you are more than welcome to check out, which explain exactly how the mechanics of how all of this work. But that's a talk in itself. And then the other bonus you get from using the data store is that you get to keep globally unique IDs across partitions. Each of your entities is uniquely identified, and you don't have to do any work to set this up. This is something that you could do with a regular partition database, but it requires some more work to set up the servers and set up a backend to assign these unique IDs, which is already built in for you with the App Engine Datastore. Some other APIs that I want to talk about are the Mail API, which uses the same routing infrastructure as Gmail, the Users API, which gives you seamless accounts integration, Images API, which does image manipulation and resizing, is used by Picasso Web to do some of their image manipulation and resizing. URL fetch, which fetches content from the web. It's used by the Gadget API. And then the task queue and XMPP. XMPP is going to use the same XMPP servers as Google Talk. So the really, really important thing the really important takeaway from all of this is that the majority of these APIs are backed by servers that are used across Google by products much, much bigger than App Engine. So there are entire teams devoted to maintaining and supporting and upgrading these services. And you get all these advantages just by using App Engine and making simple API calls. You don't have to go through the overhead of writing the code or figuring out the corner cases and things like that for your application. So with that, I want to go back to the design motivations I spoke about before and discuss a little more in detail now that we've taken a look at the infrastructure, how your application is affected by them, why we made those decisions, and what it means for you as an app developer. So our first design motivation was to build on existing Google technology. Google spent years and lots of time and lots of money working on our infrastructure, building our data centers, and also learning how to make web apps scale and infrastructure reliable. We wanted to make use of all of this in our APIs and with App Engine Serving Stack in general to give you all those benefits. You don't have to know what's happening behind the scenes with regards to all of this scaling. It just works. And so related to that, we wanted to provide an integrated environment so that it would truly be simple to develop on App Engine. For us, our motivation was based on managing all applications together. We wanted to provide one service and let you control how your application is, or give you a platform by which you can control how your application is served and how your application runs. What it means for you is that you may have to follow some of our best practices. Because you're working in an integrated environment, things may be different than what you may expect on one box running a LAMP stack. You may encounter some restrictions because of the specialization and isolation that I talked about earlier. Our tools, you may have to use and interact with our system. However, we try to make them as open as possible. But additionally, we think that they're pretty great. For example, our development environment, as mentioned in the keynote, is a 3 megabyte download that allows you to mimic the App Engine serving environment on your local machine to allow you to do development locally and then iterate very quickly in developing applications. Once your application is deployed, you can use our admin console at appengine.google.com to manage your application from one place. Because of that, you get benefits such as having your logs integrated and in one place. I don't know how many of you ever tried to correlate your web server logs with your application server logs and figure out which application logs correspond to which web requests. But it's not always so straightforward. With the admin console, that's all done for you, and it's there online and searchable all the time. Additionally, you don't have to manage or configure any machines. You don't know how many app servers your application is running on. That's all managed transparently for you. And all of these give you the benefit of ease of deployment and fast iterative development, which allows you to be a more efficient and effective software developer. So the second motivation was to encourage per-request footprints. Like I said, many applications and many requests concurrently run on the same infrastructure, the same app servers, and we wanted to make good use of our app servers and make sure that applications are fair and that we're fair in the way that we distribute resources across these applications. What it means for your application? Well, you may get less memory usage than you're used to running on a machine that you control, and additionally, less CPU. However, we think that this is a good thing in many ways because it encourages you to make better use of resources and allows you to use our APIs to do some of the more intensive tasks and not have to do them on your own machine. We want to encourage fast requests to make better use of our app servers. Again, better fairness or more fairness between applications, sort of very similar to the last slide. But fast requests also give us the added benefit of being able to do agile routing and scheduling. If a request is quick, if a request is quick for an application, we're able to move that application or redistribute the load very quickly. We don't have to wait for your requests that are in flight to complete before we can move it. It also means, like I said before, because applications are run quickly and are able to share the same runtimes, you get to make use of better runtime caching, and you may run into things such as request deadlines. Benefits for your application? Well, because of runtime caching, you're able to optimistically share state between your requests. You're going to see more throughput or better throughput and better performance in general if your requests are fast. For the same number of live serving runtimes, you're able to serve a lot more traffic if your requests are faster. You also get better fault tolerance. If you have less requests in flight at any given moment and there is some kind of failure, less of your requests will be canceled because of it. Also, additionally, better use of resources. The less you consume of your App Engine resources, the more you have to use later of our free quotas and additionally paid quotas. The next thing we wanted to do was maintain isolation between applications. So this is for two main reasons. Safety. We want applications to not have to worry about the other applications running additionally on our infrastructure. And predictability. We don't want one application's performance to impact another application's performance. This means your application may see that certain system calls are unavailable. You don't have raw network access, so you may not get some of the extensions, the C extensions in Python that you're used to using. But the benefits are you can be assured that your application is secure in the sense that no applications can touch it. Additionally, no one can SSH into your machine. You are not running on a machine that's out there on the wild. You're running behind a lot of other stuff that gives you a sense that can give you a sense of security. Additionally, you're going to get better performance because you're not running on you're not affected by other applications serving characteristics. So I also want to talk about stateless session specialization. This is something that I mentioned a couple of times, and it's really important for us in order to be able to serve so many applications in this manner. For us, it allows us to have better app server performance because we don't have to manage and maintain state. It allows us to do better load balancing for the reasons I mentioned earlier. Our App Engine front ends can move applications across web servers very quickly and manage your load dynamically because they don't have to move any state around. And additionally, because you don't have any state to maintain, you don't have any state to lose. So your application will be very fault tolerant because the APIs are what are the systems behind the APIs are what are holding on to that state. And then this means your application should use API calls to do things that are provided for you. This is really great because you get the advantage of automatic load balancing because of the better scheduling that we can do and fault tolerance. And additionally, it's less code for you to write. If you want to manipulate images or if you want to send mail or have user accounts, you don't have to write all that code yourself. You can use our backends that are specialized, dedicated systems that are the only job is to do these types of jobs for you. And then finally, we wanted to require a partition data model. The main reason for this is that we wanted to be able to give you BigTable and the Datastore. We want people to learn that it's not so hard to write applications with this data model, and you get a lot of advantages. What it means for your application is that you may have to design your data model differently than you would if you were using a MySQL database running on one machine. You will have to define indexes for all queries. But you'll see that your writes are very, very fast. Your reads are very, very fast. Your writes may be a bit slower, but you don't have to go through the pain of designing your schema or redesigning your schema or re-architecting your application. And the hardest time for an application is when your application load starts to grow. You've already done it, so you're already ready. Additionally, you get more efficient use of CPU and memory because you pre-compute things at write time, and then when you read them, it's very fast and in memory. This sort of elucidates the kind of applications that are great for running an app engine, applications that are read-intensive. Most web applications fit this mold, so we think it's a really good fit. So now I want to talk a little bit about app engine numbers and talk about some data that we haven't shared previously. So some of this was said at the keynote this morning, but currently on App Engine we have over 80,000 applications. And those applications are serving over 140 million page views per day, which is a lot of traffic. And then we have over 200,000 developers, which is something we're really excited about. We're really excited that so many people have given App Engine a try and found that it works for them and have all these applications running. And then to dig in a little bit deeper and talk about one application that was also mentioned a bit earlier, the White House had an Open for Questions application, sort of a case study in how well applications can scale on App Engine. Basically, what Open for Questions it's an instance of Google Moderator that was running on the White House's website. And what they did was they solicited questions from everyday Americans and votes on those questions to sort of crowdsource the best questions about different policy issues that were affecting the Obama administration. And in the course of over 48 hours, the application accepted 100,000 questions and 3.6 million votes, which is huge in just 48 hours. The application went from serving 0 traffic to having 3.6 million votes and 100,000 applications in just under 48 hours. And then at the end of all of this, President Obama, in a live televised press conference, answered the highest rated questions from some of those topics. This was really exciting for us and really exciting as App Engine developers, as Americans in general, to get that kind of interactivity between us and government. So you can take a look at the graph. You'll see that White House kickoff blog posts, whitehouse.gov, got a little bit of traffic. 100 QPS of traffic is actually kind of a lot of traffic. And then in the afternoon, we got a mention on NPR, New York Times coverage, and CNN coverage. And then at 5 o'clock, there was a link on the Google homepage for the White House's application. And then before submission, this application peaked at a load of about 700 queries per second, which is a very, very high amount of load. And then they cut off voting, and the traffic came down really quickly. And so with that, I'll open it up to questions. I'll pull up the moderator page, and if you want to ask live questions, you can walk up to the microphones as well. Thank you. That's weird. All right.
I'm curious about what you were just saying about Google Moderator. If you guys developed that in-house and deployed it on behalf of whitehouse.gov, or if it's an open source project that you had previously built that their developers deployed without any sort of changes that you would have had to make to scale to that size.
So Moderator is an open source project that is available for anyone to deploy. The White House made a few changes for a variety of different reasons, privacy and increasing performance. They wanted to really get that tuned as best as possible. But they deployed the application, and it's there for anybody to download and deploy their own.
Did that take much work from you guys for them to be able to get it to scale to that level?
We were there to support them, but yeah. I mean, it was really important for us, and we kept a close eye on it to make sure that it went well. But yeah, it was a really big success. And additionally, it didn't impact any of their applications serving on App Engine, which was huge.
Hi.
Yes.
You talked about several Google applications that we can use as part of the App Engine, like mail and chat and those kinds of things. Is there a plan to give something like a search itself as an application?
Search itself as an API?
As an API.
So we would very much like to have full text search on our data store. Because we sort of are rethinking the way that we do certain things in order to make it available to lots of applications, and on a request-based model, we've had to sort of redesign some of the things that you sort of take for granted that Google's good at, like search. All I can say is that we're working on it, and we'd very much like to have search in our data store.
Great,
and
thank you.
Yeah, you're welcome. And then I'll take some of these questions here. I'll take one question up here first. I don't know. This looks like, yes. Is there a way to preload big libraries such as Django 1.x rather than delaying requests for several seconds while ZipServe loads it? So like I said, you can take those libraries and use your runtime caching. So if you use a main method in your Python, we will cache everything in your global space for the next request on the same app server. So while I don't know if there's a way to preload big libraries so that your first request has them already in there, already like hot and on the app server, subsequent requests should see an increased performance. Yeah.
So it seems like from this morning's demo, you're making a big effort to integrate GWT, and particularly the Eclipse plugin and all of that stuff with App Engine, which is awesome. But it makes me wonder whether that's not going to leave the Python runtime behind. Is there any plans on the roadmap to do the same kind of one-click magic stuff in Eclipse that we saw this morning?
That's a really good question. I don't know exactly what is in the plan. I'm sure we'd like to do things like that, but there's nothing on the roadmap at this time. I'll take another one from here. In order to take advantage of application caching, should you avoid inline imports in your Python code? How do you ensure your code is cached optimally? That's a really good question. So it's sort of a trade-off, right? If you put all of your imports at the top of your Python code, all of your imports are going to get imported on your first request, and they're going to hang around on the app server cache for your runtime and be available to the next request. However, that's going to make your first request much slower. If you break up your imports into only the code paths that need them, you'll be doing less than a per request basis. So that's more of like more of something you need to figure out for your application and see what works best.
So you've done some work to avoid hitting the App Engine all the time, so like serving static files or doing the image access. There's pricing for like Gmail sending mail through that API, but how do you price serving static pages? Is that just free, or does that count as compute cycles, or how do you kind of calculate all the API usage and static usage?
So we still charge for bandwidth in those cases, but you don't consume any CPU cycles, which is the most expensive resource that there is that we have. Yeah.
Could you talk a bit about data portability and moving data in and out of the BigTable data store?
Sure. I can mention it briefly. We have some libraries, our bulk uploader and bulk downloader, that will get data in and out in a common format. I don't know, and those are available and on the website for you to use to get your data in and out.
Okay.
Yeah. Is there anything more specific, or?
Not in particular, but if you have maybe an example of a company that has like multiple systems, maybe partially built on App Engine, and then they have maybe something on Amazon systems. Do you have experience with that?
Mike, do we know any such companies that have data on App Engine and port their data between EC2 and App Engine?
Yes, in fact, we have a talk from law school and App Engine partners. Tomorrow they're showing actually kind of a hybrid scenario where we use EC2 along with App Engine.
Yeah, so the talk. App Engine nitty-gritty was the talk. It's going to be on later today.
Thanks.
Yeah, welcome. Take one more from Moderator. I see Datastore timeouts seemingly without any difference in my deployed code or usage patterns. Is there a way to get more information about why the Datastore is timing out? So you can take a look a little bit. Your logs will give you some indication of when your Datastore is timing out and some of the reasons based on if there's contention, that'll show up in the logs. And there may be some other reasons. I encourage you to go to Ryan Barrett's talk on the App Engine Datastore and ask him these types of questions because he's really the expert on it. Please.
Hi, Ert Dredge from Universal Metaphor. Can you outline if there's any significant differences between the Python and Java flavors that you have either right now or in the roadmaps, or are they, as far as the restrictions you get for App Engine, are they pretty close to the same capabilities?
Well, we want to try to keep both of them in line as far as their capabilities, and we continue to update and maintain API level equivalence between the two. I don't know specifically. Is there anything specific that you were?
I'm right now agnostic and actually looking at choosing one versus the other, and I was wondering if there's, well, yes, we're planning on having this capability on one side, or Java hasn't yet caught up to that capability, if there's any major differences you know about.
I think that we're committed to maintaining the same capabilities across both runtimes, yeah.
Okay, thanks.
Please.
This is another zip import kind of app or module caching question, but you mentioned that the App Engine will cache the module for that application on the same app server, and many people have kind of found out that those modules are cached for a number of seconds, but after a few seconds of not having a request, that module will get kind of dropped. And so also if like the application, or if it's cached for that app server and you have multiple app servers in the App Engine infrastructure,
sure.
Like how many requests per second basically would you need to have before like you would basically not have to import the modules every single time, or not expect to like have users getting slow requests?
Right, that's a good question. So basically, what kind of sustained requests per second would you need to keep your runtime in the cache? I don't know if there's really a specific answer to that, because it sort of changes dynamically, both with the amount of traffic that we're seeing across all of App Engine, because caches will get cycled out as more requests come in, and they're handled sort of in a first in. They're handled. We handle them equivalently, so I don't know if there's a specific answer in terms of like a number I can give you regarding that. Excuse me? Yeah, I really don't know. It sort of depends on your application load too, because once you start seeing more traffic, you may get scheduled on more app servers, which means that you'll have more caches to maintain hot, and it's, yeah, I really don't know. I really can't answer that question. We'll take one from Moderator again. With the App Engine Datastore, can I control where my data is replicated in BigTable? For example, if I don't want my data to be replicated outside of the US or conversely into the US, can I pin the data to a specific geolocation? So in general, regarding data replication, your data is replicated, and currently I don't think we would like to give developers control over where their data is or where their application serves from. And we're working on that, but we don't have that capability right now. So EU requires data to stay within the EU. I'm sure that we abide by the various laws, but I don't know the specifics regarding that, though. So yeah, let's take another question.
Michael Pastushkov, Dynamic Software. You addressed a great deal of scalability issues. Thank you. What about complexity of the application? How complex the app would be? That's question number one. Question number two, what about background housekeeping kind of thing? Is it possible at all? Because the more complex the application, you definitely need it.
Great. Both great questions. So in terms of complexity, because you're using APIs, which take some of the complexity out of the scope of your application and push it back to dedicated services, your application or the code that you deploy can be much less complex because you don't have to do that work yourself. And then secondly, in terms of background processing or offline processing, we have it on our roadmap, and we're giving a talk. I think it's tomorrow is Brett's talk on offline processing, a look ahead, and he'll give you a look into the different kinds of things you can do offline. Actually, although right now we do have cron support, and so you can use that to do that sort of outside of the scope of request processing. Yeah.
David Ellsworth, Ogopogo Web Pages. Do you have equipment operating in China?
I don't. In general, we don't discuss the location or any details regarding the data centers, so I cannot be able to answer that. Thank you.
Yeah. When I want to implement App Engine for an enterprise and which has a brand, if I want to disable the AppSpot URL, is it possible? I don't want to hide the implementation of, like, let's say I created an application called branch.mydomainname.com, and I don't want that branch locator or whatever the name which I use as an app ID that I can access basically using applicationid.appspot.com, which if I want to hide it.
So do you want to hide that exists, or do you want to hide that the content that's on the site?
I want to hide the AppSpot URL, and I want to just use my brand name, mydomainname.com / some application name.
I see. I don't know exactly what you can do for that. If you're concerned about revealing your website before it's ready, you can deploy a second major version and then have the default version display some sort of static content or some sort of placeholder until you're ready to switch it over. But I don't know offhand how you would go about disabling AppSpot. Yes?
For example, like I have an application which says like, let's say application name.mydomain.com. So when I create that application ID, even I can access the same application using application id.appspot.com.
Right, so you can do it in code. Let's talk more offline.
Okay, yeah, thanks a lot.
Yeah, and then I'll take one more over here. Well, I'll take two because pretty straightforward. The first is, are we planning to provide a way for deleting an application? We would very much like to provide a way to delete an application, but it's on a long list of other things we'd like to do, and it's just not at the top of the priorities right now. So, yeah, at present, no, you can't delete an application, but it's definitely something we'd like to provide. And will this presentation be available online? Yes, it will be. I think it'll be on YouTube, but I don't know specifics on URLs or stuff. I'm sure it'll be in the conference material.
Are there any plans for being able to establish a trust relationship between a couple data stores so you can make requests across those, or is it always going forward going to be distinct? You can't from a security perspective?
It's definitely something we've talked about, and I think it's something that is really valuable. I don't think that we have any plans to do that now, but we're definitely thinking about it. And again, if you want to talk to Ryan after, he may be able to give you more insight into that stuff.
Hi, my name is Scott Leahy. Thanks for taking my question. My question is around the economics of App Engine. As an example, how much would it have cost to run that White House application for a developer? And is there like a cutoff point where, that Google's thinking about, or that is kind of the de facto where you say, hey, once you're, kind of hit this level, economically it makes more sense to sort of move off the platform onto your own thing?
Right. So I don't know specifics about how much it would have cost, or how much it would have cost to run the Open for Questions White House app. In general, I think we have about 5 million page views is what we shoot for. It obviously depends on how you write your application. For the free quota, which is absolutely free, and then 5 million page views per month. Is that right? Yeah, 5 million pages per month. And then secondly, to the second part of your question, which was regarding how high an application can get. So there are some limits in place that are safety limits that an application, so that the peak that an application can serve right now. But if you want to exceed past those limits, feel free to contact someone on the App Engine team, and we can definitely talk about those. Those are just in place sort of as a safety measure and can be removed on a case-by-case basis.
Thank you.
I'm curious, I know that when you had problem serving a couple of months ago, they were saying that applications with a certain profile, if they were more dynamic or static, would hit limitations when others would serve just fine. Are there certain best practices that you should maintain in the event of an outage or something to where you could have static fallback content or something like that?
Sure. Yeah, definitely. Static fallback content is great. We have certain APIs may throw capability exceptions, which you can catch and then handle. So, for example, if during certain periods we may go into read-only mode for the data store, or your Memcache may be unavailable for some reason or something like that. But those APIs will throw specific exceptions for those cases, which you can then catch and then handle appropriately.
What about something like letting Python manage your URLs? If the Python app server goes down, then your entire app goes down. Or if that were an app.yaml, I don't know if that would reroute to static or if there's...
So the app server going down entirely isn't really something that we are... So that's not really like the big concern. It's more... I think the cases that you're talking about were very specific to maybe a set of API backends that were available. And so just using those in a robust way and following some of the best practices that I think, in terms of scalability also, which I think are going to be covered in a talk later about building best practices for building scalable apps.
Cool, thank you.
Yeah. So I've seen a Google application app run Google App Engine app run very slowly. This is an application that worked quickly and has very few users. Can you describe what causes this and what we can do? Is it because of a big bandwidth user such as whitehouse.gov? So first off, it's not because of a big bandwidth user such as whitehouse.gov. Because of the isolation that I talked about before, applications don't really affect the way that the other ones serve. So specifically, it's very difficult to say from this much information. It could be a variety of different reasons why your application may run slowly, even though there are a few number of users. If you follow our best practices, hopefully you can get around that. And there's at least one talk today or tomorrow, I'm not sure, about how to do that effectively.
Yeah, I was interested in if there was any plans for parallel URL fetch, basically, if being able to request, if you only have 30 seconds to run and you spend half of that blocking, if there are any plans.
So that's definitely something that's definitely something that we want to do. I think that it's available, is it? I don't really know. Soon. Yes, soon, if not now.
Yeah, one thing that we've observed occasionally is the very front end of the App Engine kind of goes haywire, and you get, errors that basically don't then occur you don't see in the App Engine logs, basically, because it's at that first level of the tier that's erroring out. Is there any plans or thoughts about? And I don't think those generate the same kind of like alerts that you might get.
Right. That definitely does happen from time to time, and there are a variety of reasons why that may happen, and there are factors that contribute to it based on whether you're serving off of AppSpot or you're serving off of a custom domain, because those different requests will take different paths getting to App Engine. And so I can't speak to specific cases, but there are some factors, some of which are in our control and some of which are not, since we're customers of a lot of services inside Google also. Let's see. So I'll answer one more from here, and then wait, which one? Oh. Right, new applications with a low number of requests really suffer from a lack of application caching. Do you have suggestions to improve app spin-up time, and/or can app caching be adjusted for these low-traffic apps? So for those low-traffic apps, one of the things you can do is not do all of your importing and initialization at the top of your function or at the top of your requests script, and do it only for those paths which the request will follow. So doing inline imports and things like that may help. So I don't know what the best practices are for Java. I think there's a talk that's Java specific going on for App Engine a little bit later today. And
it's the next talk.
Oh, great. Next talk, that would be the right place to ask that question for Java.
When you were mentioning that hot apps keep the memory around, specifically, how do you take advantage of that? I would assume Memcache is one way. Imports are probably hot, but does that actually apply to variables within Python instances? It does. So It seems like it changes the programming model a little bit. How would you best take advantage of those instance data or that is actually around for you?
So for Python specifically, or Matthew's got? Yeah, so we can talk more about that specifically. Oh, we're going to be holding office hours across the way, and you can come to us with specific questions, but I've got to wrap it up anyway. So thank you all for coming.